Hello everyone, thanks for watching my presentation. Today I'm going to discuss my work, the CFD analysis of a twin screw compressor with oil injection. This is a joint work between Simerex and the City University of London. In this presentation, I'm going to follow this outline. First, in the introduction section, I'm going to just briefly go over the problem, including the advantages of using oil-flooded twin screw compressors and the numerical challenges for simulating such problems. Next, I'm going to discuss about the modeling approach in Simerex MP+, including the governing equations like mass conservation, momentum equation, and then the energy equations, and also the WLF approach for multi-phase problems. And also, I'm going to discuss about the twin screw rotor mesh and the inlet-outlet port meshes. In the third part, I'm going to introduce 3 test cases and discuss the results from the numerical simulations and the test data and try to compare them. At the end, I'm going to give some conclusions of this research work. The first part is the introduction part. A rotary twin screw compressor with oil injection is commonly used in industry because it's very compact and reliable. There are 3 functions of the oil. The first function, which is the most important function, that the oil can reduce gas and the rotor temperature to extend the life of the rotor. The second function is that the oil can seal clearance gaps to improve the volumetric efficiency. And the third function that the oil can lubricate rotors and bearings. However, there are some challenges for the 3D CFD simulations. For example, the first challenge is that the rotor is a complex deforming fluid domain, so it requires very robust mesh generator for the rotor. The second challenge is at the modeling side, because this is a 2-phase flow with a complex moving paths and small leakage gaps, so it requires very careful modeling of this problem. Generally, the 3D CFD simulation will have like very poor convergence and a very long simulation time and unsatisfied mass and energy conservation. Although facing these challenges, the Simerex MP+ can do a good job. For example, Hui Ding and Jiang Yu in 2017, they published a paper titled with CFD simulation of a twin screw compressor with oil injection. A good result was obtained in that paper. In the second part is about the modeling approach in Simerex MP+. In the solver, we solve the mass conservation and the momentum equations and also the energy equations for the gas-liquid mixture. And also for the multi-phase, we use a volume of fluid WLF model. The twin screw compressor rotor mesh are generated by the squark, and later on, these meshes are read into Simerex MP+ at each time step. If you want to know more information about the squark, you can refer to these 2 papers. And for the inlet and outlet port meshes, they are generated by the built-in binary tree mesher in Simerex MP+. Also, one thing I want to mention that the axial end gap can be included in the model without causing any divergence or sacrificing the running speed. But for the comparison purpose, So we didn't include the axial in the gap in this particular model. For the case study, we use N-rotor profile. The male rotor has 4 lobes, and the female rotor has 5 lobes. Totally, we have 3 cases. The male rotor speed ranges from 3,000 RPM to 6,000 RPM, and the suction pressure is set at 1 bar, and the suction temperature is set at 298 K, and the discharge pressure ranges from 6 bar to 8 bar. And the oil injection pressure is at 0.5 bar lower than the discharge pressure. Also, the oil injection temperature is set at 323 K. Here is the overview of the 3D CFD simulations in Simarex MP+. The total number of cells, including the pores and the rotors, is about 0.8 million. The male and female rotor about 0.4 million. For the inlet and outlet pores, it's about 0.4 million cells. Also, the discharge pressure is gradually increased to the designed pressure within 4 full male rotor rotations to achieve the best stability. Also, the results becomes periodical within 15 revolutions for all simulations. We also checked the mass imbalance for the air, which is below 3%, and also for the oil is within 1.5%. For the simulation time, it takes 2.4 hours per revolution on 6 cores. If we use 24 cores, the time will be reduced to about 0.8 hours per revolution. First, we compared the air mass flow rate, shown below. The blue bar indicates the test data, and the red bar indicates the Simarex CFD results. Also, you can see that for the case 1 with 3,000 RPM, 6 bar, all Simarex CFD results is like roughly about 3% below the test data, and also for the case 2, our results are also roughly about 3% lower than the test data, and for the test 3 with 6,000 RPM and 8 bar, all results is about 4% above the test data. Generally, we can conclude that a good agreement is achieved between the CFD simulation results and the test data. Next, I'm going to discuss about the indicated power. Similarly, the blue bar indicates the test data, and the red bar indicates the Simarex MP+ results. For the case 1, Simarex MP+, the CFD results is overpredicted about 2%, and for case 2, the CFD results overpredicted roughly about 6%, and for case 3, also overpredicted roughly about 7%. However, we should keep in mind that the test data here is calculated in this way. The measured shaft power multiplying the mechanical efficiency, which is 70%. Here, the 70% mechanical efficiency may overestimate the mechanical loss, and that's also the possible reason that the CFD results overpredict the indicated power. Overall, we can conclude that the CFD simulation results matched well with the test data. In Simarex MP+, we developed a method which can track the target pocket. For example, here you can see in this animation, we can show the development of the target from beginning to the end. The 4 pictures on the left shows the temperature, shows the average temperature at the different stages. And we can also display the pressure and the temperature on the single pocket. And based on that pocket tracking, we can plot this PV diagram, and also we can compare the different performance of the different design. Here we show the oil distribution for case 2 at the different rotation angles. The blue color indicates the air, and the red color indicates the oil. As you can see from these 4 pictures, that the oil accumulates in the rotor tips and also in the discharge parts. Here we also show the oil surface with a volume fraction bigger than 0.1. And here the animation shows how the oil is distributed within the rotor. As you can see that the oil is released from the injection part and carried over by the rotors. And here we also show the temperature distribution for case 2 at the different rotating angles. As you can see from the left 4 pictures, that in the higher oil contribution area, the temperature is lower, and in the lower oil contribution area, the temperature is higher. We also monitored the oil mass flow at the discharge. This plot shows the instantaneous oil flow change with time. As you can see, for the case 3, with a 6,000 RPM and 8 bar discharge, the oscillation is quite big. Sometimes the oil flow rate almost 0 at some point. We also checked the average temperature at the discharge. The left panel shows the temperature. As a comparison, the right panel shows the oil mass flow at the discharge. As we can see that the temperature is closely related to the oil mass flow at the discharge. For example, if we check the case 3, we can see that when the mass flux reached almost 0 at the time step 40, we can go back to check the temperature. We can say that at the same time, the temperature reaches the highest peak around 370 degrees. This clearly shows the cooling effect of the oil in the twin screw compressor. Finally, we have some conclusions for this research work. The 3D CFD simulations for oil-flooded screw compressor were carried over using Simax MP+. The simulation is quite fast. It only takes 2.4 hours per resolution on 6 cores. If we use 24 cores, the simulation time is reduced to 2.8 hours. The mass imbalance for air is below 3%, and for oil it is within 1.5%. The gas mass flow rates in Simax MP+ have a good agreement with the test values in all 3 cases. The indicated powers obtained by the Simax MP+ show a well match with the measured shaft power. The averaged pressure in compression pocket is tracked, and the pressure volume diagram is also plotted and compared for all 3 cases. Oil distribution clearly exhibits the cooling effect on the temperature distribution.